Hello, I'm George, and I am going to present you today the MBMT-Net, as we call it. This presentation contains a few aspects about the introduction to the convolutional networks, then some background in computer vision and deep learning. We're going to present data set and show the results of the analysis and eventually the feature enhancements. Okay, so first of all, what we have to keep in mind in this presentation is that the convolutional neural networks are usually developed by researchers so that they have more performant building blocks so that they can eventually perform better and have more robust feature extraction means. So however, these kind of improvements may be insufficient in a way that we consider because the problem itself of solving some dense tasks that suppose that we predict a whole mask of pixels or something like this with the same resolution as the input image. This context of learning may be difficult for the network, and the problem may be therefore ill-posed or suboptimal, at least. And we are thinking of introducing an architecture or a design of building convolutional neural networks such that we can overcome these problems and eventually consider having more feature extraction means and more reliable networks. So yeah, this is the most relevant thing we are going to continue with, namely the convolutional neural network and the encoder-decoder architecture. So far you've been pretty comfortable with the convolution, I guess, from the previous presentations, and I'm not going to insist on it. Basically, what we want to underline is that these networks usually have an encoder-decoder architecture, as seen on the middle image from the right, so that the encoder is responsible with extracting the features and compressing them without losing crucial information, so that the decoder can then reconstruct the image and offer us a prediction according to the task we are performing. And on the bottom image, we can see a convolutional neural network that has a more sophisticated architecture. This is the efficient PS, the panoptic segmentation architecture that we are going to use a part of it in our research. And this is also based on an encoder-decoder architecture, and our research also mostly spins around this concept of encoder-decoder, because we are going to try to introduce this MBMT network so that we can see how the multi-backbone multitask networks would act and how they perform if they have a common joint learning context, and how the performance would enhance in this situation. And for that, we are going to use the new data set with three different, and we are going to perform 3 different tasks in both the single task and multitask contexts: the semantic segmentation, depth estimation, and surface normal map prediction, which we are going to describe later, and see how our networks architecture, especially regarding parameters and efficiency, would compare to the state-of-the-art approaches that we mentioned here below. So as a related work, that is what we have here is the efficient net, which is the backbone we are going to use, and also the efficient panoptic segmentation network that I showed you earlier uses this efficient net backbone. This allows us to use pre-trained and pyramidal features that are extracted by the backbone. And these multi-scale features are usually better than a single resolution, single scale feature map because we can use them together with some other skip connections in order to reconstruct better the image with little to no loss of information. So then what's another important thing is the CBNet, which is the composite backbone network. There are two of them, the V1 and V2, which implement something similar to us. However, they rely on using the same architecture for the backbones, and they use something like flattened RNN model, meaning that it offers higher level features into succeeding backbones, which increases the performance and minimizes the loss of the extraction means. And another important thing is the multitask attention network that is the current state of the art in multitask performance, and we are going to compare our results with it. And an important thing to keep in mind is the dynamic weight average procedure that is used by us and introduced by them, so that the convergence speed of the tasks are about the same, so that we do not, if we were to have a much simpler task, like not dense task that supposes to create a mask, as we have in semantic segmentation, we have to alter the mask. If we were to have a classification task such as indoor, outdoor, or something like, I don't know, cloudy or sunny kind of classification, then that task would pretty much be learned instantly, and it would overfit in the end. So this DWA thing is used by us to grant that we do not overfit our network. Okay, so another thing is the learning context that we are going to use. Usually, most of the networks have single task. Are using single task learning contexts, and this is beneficial because they have lower number of parameters, and they usually are capable of achieving state of the art by themselves. However, if we were to introduce the composite backbones, then we'll have the boost of confidence in feature maps, and the extraction means would be better in this way. However, this is problematic because the number of parameters increases with the number of backbones that we use, and we aim towards minimizing the use of parameters such that we end up with having the same number of parameters as a regular multi-task single backbone network in our MBMT-Net. And speaking about the multitask models, there are two architecture types for this: the soft sharing and the hard sharing parameters. And the soft sharing presupposes that we have like interconnected layers that share parameters, but they are more sophisticated, and we are going to aim to use hard parameter sharing, which supposes that we have a single backbone with multiple heads, parsing heads, task-specific heads, that are going to learn the specifics of each task, while the shared backbone tries to extract generalized features from each of the models. From each image. Okay, so the multi-backbone multitask model in our approach combines these several approaches of multiple backbones and multitasks, while reducing somehow the number of parameters used. And also we aim at using multiple architectures by themselves. This is only the idea, the architecture design, and not exactly, it is not restricted to having certain types of backbones or certain types of heads, which implies that we could extend the use of our network to make use of implemented better backbones and better heads with different kind of with different depths, so that we could basically implement any tasks and use it in any context with multiple or single or however many parsing heads and backbones. Okay, so the data set is offered by the multitask attention network. We have it from their GitHub. They have preprocessed the images by dumping them as NumPy arrays, which is easier to read, but the images themselves are similar to what are found in the original data set. And the resolution is pretty low, but regarding this is more like a proof of concept. It is enough to prove our point, and we suppose that we are going to implement multiple experiments on different data sets later if we are going to extend the architecture itself. Okay, so these are some examples from the data set. We have the raw images on the left column, the RGB images, and in the middle we have the depth masks, which are supposed to have the depth distance, the distance from the point to each point from the camera, so that we know what distance there is from the camera to each object in the frame. And on the right column, we have the semantic masks, which are supposed to show us what kind of objects are in the frame, so that each point belonging to an object should be of the same class. As we can see, there are pillows, walls, tables, and many more objects. And eventually, we're going to present the tasks in depth. So the semantic segmentation, as I said, has to output a mask that tells us what kind of object we have in the scene. The depth estimation is usually a regression task and is used to output masks containing continuous values from 0 to whatever the maximum is, like 300 or something for outdoor scenes, or even less, like 50 for indoor scenes. And it outputs a one channel image, which has the actual depth. And the surface normal prediction supposes that we have in each frame the angle of the surface normal to the objects. Like they are usually used in video games. We have the surface, and we have to output an RGB image containing the angles in an XY, X, O, Y, Z system, so that we know what angle the surface faces towards, and we can detect therefore surfaces together. Okay, so in the experiments, we're going to keep the abbreviations of the models so that we can refer to them more easily. Basically, there are 3 single task networks that perform the task of choice. They are based on EfficientNet B2s, and the multitask network has a greater EfficientNet B5. And our multi-backbone multitask network has 3 EfficientNet B2s to show the potential of this EfficientNet and also keep the number of parameters low. So eventually the comparison is fair and the number of parameters between the multitask and multi-backbone multitask is about the same. Actually, in the MBMT-Net, we have 98.19% of the parameters from the MT-Net. And this is the architecture that we are going to use. We have here the 3 backbones that are task specific. Each of them are going to be trained for each of the tasks, pre-trained or trained together, or only one would be used in case of the MT-Net. So for the MBMT-Net, as we have here, the 3 backbones are going to be concatenated channel-wise into feature maps that are going then through the rest of the efficient panoptic segmentation network with the 2-way feature pyramidal network. And then here we have the task-specific heads, the semantic segmentation, the depth estimation, and the surface normal map prediction. The DE and the SNP heads are similar regarding they have the same number of layers, but the output channel number is different. As I said, for depth, we have only 1 channel, and for surface normals, we have 3 channels because the images have to be RGB. And for semantic segmentation, we're going to have the number of classes times the resolution of the image. Okay, so regarding the training, we've performed multiple experiments, and we're going to present a few of them. And in tables later, we're going to show only the relevant ones, because we've learned that some of them do not actually provide any additional information to the tables and to the research itself. So we've tried training the single task networks, then the multitask network with bigger efficient net. We tried to train the MBMT-Net with both the B2 and B5 to see how it performs. The full training means that we do not freeze the weights, which eventually ends up with us having pre-trained encoders and stretch encoders, and we train them so that we can see how it acts and how it learns. And we decided that the gradient propagating through the backbones almost outputs the same feature map extraction means, which did not provide any help. However, if we partially train the MBMT-Net, it means that we have frozen the backbones, and the backbones have been each pre-trained for task specific. For each task, the semantic segmentation, depth estimation, and surface normal map prediction. And then the rest of the network has been trained together. And the metrics are pretty standard. We are going to use, you are going to see them more in the tables, and I'm going to describe them along the way. And here is the first table. Along these metrics, we are also going to take a look at the number of parameters. As in our training schedule with the MBMT-Net with the frozen backbones, we see that we have an even lower number of parameters than we have in the efficient panoptic segmentation networks. So that this means it could be a good approach if we aim to train on lower end GPUs. And regarding the total number of parameters, it is a little bit lower than the multitask network, and still a lot lower than the multitask network, which is the state of the art. And here is the performance compared to the rest of the models. As you can see, the MBMT network completely outperforms the multitask network in each of the scenarios. And it even surpasses the state of the art regarding the MIOU for about 4%, say, but it still lacks a little bit on the other scenarios. But it regarding the number of parameters of the MBMT-Net, it is quite close to the state of the art, and it is probably even going to surpass it if we use the same number of parameters. So here we have the relative improvements. As I've said, we have a lower number of parameters. The losses of each task specific is just like a guideline to see how they perform. And for the MIOU, this means that the objects detected in the semantic masks are used to, are overlaid well with the predictions with our actual ground truth. And however, the pixel accuracy is a bit low because it may have some problems because of the number of parameters. And I guess these are the limitations because we aimed to lower the number of parameters and see how we perform against the multitask network. And in surface normal maps, it's a bit more difficult. However, it is pretty close to the multitask attention network. And as we can see, it dramatically outperforms the multitask network or MBMT-Net. So this is a good sign that multi-backbones may help us overcome some problems, and it acts like a regularizer, and also it performs well in this multitask context by providing us more robust feature extraction means. And as I've said, the multi-backbone has shown its power and its potential in our experiments. The MBMT-Net has a lack of a deficit of 12 million parameters. However, it reaches state-of-the-art performance and almost surpasses it in some points. However, there is still a lot of more to be improved, and we aim at understanding the distributed AI potential of this model, and we're going to search for more tasks and more contexts to train our network. I'd like to thank Professor Cibula Gabriela for her help for the work, the research, and also my colleagues at Bosch, and thank you for your attention.